Okay, we have 12 people. That's about, I mean, a good number. You usually start with 15, but reinforcement learning, and especially when it's upside down and the slides, why are the slides upside down?
Well, to correct for that, I did have a right side up as well. Yeah, let me know when you all are ready.
Please go ahead.
Great. So today we're going to be going over the Jürgen Schmidt-Huber paper with the training agents using upside down reinforcement learning. Specifically, this was given as a talk in the NeurIPS 2019 deep learning workshop. This is further work done by previous analysis by Schmidt-Huber on a couple different papers building up to this workshop, and then further analysis is done through the archive paper, trying to compare similar works. Today, what I'm going to attempt to do is go through basically a very brief overview of what reinforcement learning is again, why this is even called upside down reinforcement learning, and the new approach that they attempt to conceptualize, go through some of the mathematical formulation of it, a couple examples, and then some results on the various games that they use as standard for reinforcement learning. I'll then follow up with some related works and some open questions that this new field of reinforcement learning presents itself. So to start off with, what is reinforcement learning and why does it matter? This is specifically the mathematical formalism for learning-based decision-making. It's an approach for learning-based decision-making for control from experience. So the main idea is quite simple. There's an agent with an algorithm interacting with the environment through actions. These actions make the environment respond with a new state and a signal, the reward, that the agent will then use as feedback, and the learning happens through trial and error. If the signal is negative, the agent learns that it shouldn't be doing that, and if the signal is positive, then it learns that it might be a good idea for actually to do that the next time. The reward is really the key for the agent to learn, which is the sequence of decisions that are best. So from standard machine learning, we're given some set D given an observation and action. We're learned to predict Y from X, usually assumes IID data, where we know the ground truth outputs in training. For reinforcement learning, we know that the data is not IID, as previous outputs really influence future inputs. So the ground truth answer is not known, only if we succeed or fail. So more generally, we know the reward of what we're trying to achieve. And so specifically, deep learning has helped in many of these cases, as a lot of these problems require quite a lot of data to actually learn either the Q function or how to approximate the action decision pair that is needed to generate the output given the action in the environment to perform on the algorithm. So as a couple of examples, these are either the Atari games or different types of backgammon games or real life examples of the of a walking problem where the agent will then make a decision on the environment, has consequences with the observations with the reward, and then iterate through this loop of or this iterative loop of cycle. Now, when approaching upside down reinforcement learning, usually we have this Q function where there's a pair of observation and action, which is then put into a Q table that generates what the optimal value for the expected return is. Back in December 5th, 2019, Jürgen Schmidt-Huber and his team came up with this revolutionary idea of upside down reinforcement learning, where they published in 2 papers. Traditional RL either predicts the reward of the value function, i.e. the Q learning, or maximizes them using a policy search, typically policy gradient methods. They propose something that is different, where instead you're predicting the reward using it as an input rather than an output, along with the state to map to the actions, literally turning reinforcement learning upside down. I am sliding way too fast, sorry. in this sense, they denote it like I have here, although I believe Sergey was right that it is also mirrored as well. But that is how they denote it within the paper, which is very cheeky and fun. And so instead, upside down reinforcement learning has a function approximator that maps the state action pair to values as the expected return, which is called the behavior function, or B in this case, that maps the state command to the action. And what is a command, you might ask? There are a couple interesting things. A command consists of the desired return in the desired horizon, where the desired return is the length of the state action space, and the desired return is a chunk of that space. To get a little more formal, the agent to be given to a command indicating that the return of dr, or the desired return, is the next step in the desired horizon, denoted dh. So the behavior function gets an action, state, desired return, and the desired horizon. We here let S and A be random variables denoted in the environment state in the agent's next action, respectively. We denote R of D as the random variable denoting the return obtained by the agent during the next desired horizon time steps. Then the behavior function produces the conditional probability that taking an action of A and thereby acting using the policy denoted as pi here, that leads to the desired return and into the desired horizon. Here we assume that instead of a policy, only a data set of trajectories generated, or denoted T, is then generated using unknown policies are available. And we are interested in the behavior of the behavior function given the set of trajectories for the data set. With discrete states and actions, we can then estimate from the available data. Here we have n of t of k of a, just to explain the third equation quickly. The numerator is the number of trajectory segments in T that start with state S and have length the desired horizon, with the total reward of the desired return. And, or sorry, that is the numerator. So the numerator is the number of trajectory segments in T, where the denominator is the number of such segments where there is reward given the action. As a quick example, oh, go ahead.
Sorry, the b pi, that's like a objective function, right? Like a loss function, because you give a as the input, right? So that's you like.
Yes, absolutely, and that will be more formalized as the algorithm input that'll have about 2 slides from now. But you're absolutely correct.
How do you have? Sorry.
Go ahead.
How do you have all the actions? So if you have all the A as the input, you just know them a priori.
You are going to be randomly sampling all of the actions and then rank order the best in the replay buffer. So the way that you store the best actions given sort of your exploration, you will be stacking in order of best reward. So the actions will then be assigned based off the reward given the number of steps. So your choice in sort of the trajectory is important here. So the desired horizon in this aspect is designing whether or not you can actually get to a space in a given time step. So it's not necessarily just going to an infinite horizon, which a lot of reinforcement learning algorithms tend to do. But instead it's saying, can I get a reward of 5 in 3 time steps? Does that make sense? Instead of, can I just get a reward of 5?
And which action leads to that reward of 5, right? Like it's like,
yes.
So you're trying to predict like, okay, if I want to get a reward of 5 and be in this certain horizon, then what action should I take to obtain that goal?
Yes,
right?
Maybe that'll be more clear in the example that I have on the next slide. I have 2 examples. This is the very toy problem that they present in the paper, and then I produced a different example to sort of help with this. So here is a simple Markov chain with actions, rewards, and states. We have 2 terminal states, S2 and S3. and we could either be in S0 or S1 to reach those terminal states. Now, according to the MDP, we were to explore the environment, we could end up building the table as shown. If we were in S0 and wanted to get to reward 2 in one time step, we would take the what action will we take? Well, we would look at the MDP again. We should get action 1 as the correct step. That would give us a return, or give us 2 as a return in one step, landing in S1. How do we go about getting 1 in one step? Well, since we're still in state 0, we definitely do not want to take the action of 1, or of action 1, as we saw that the action gives a return of 2 in one step. From there, we can take the action that gives the result of 2 in one step and then get to action 2, landing in state 2. Now, this is going to be a command for the agent to get a reward of 1, but this is still done in 2 time steps, which action would be take in terms of that step. Well, we would then keep going either from S1 to S2, S3 to S1, and then sort of surmise what the desired return would be given the horizon for the action to be able to be taken. This maps to the identical action that must be taken to comply with command 1. Here we have the different features of the state, desired return, and desired horizon, and the labels are the actions, which is exactly supervised learning. What upside down reinforcement learning claims to do and is a nice bridge between reinforcement learning and supervised learning, which supervised learning has been proven to be quite stable and successful. However, upside down reinforcement learning turns this idea of reinforcement learning into a supervised learning problem, training an agent on all the past experiences in a supervised way. So using both supervised learning and reinforcement learning problems isn't quite new at all, and a lot of these ideas have been previously conducted in imitation learning, but with little success. And so this paper in this introduction leads to sort of a quote done by Bartow and Uterich from their textbook in 2014, that in general, there's no way to try to bridge these 2 concepts. However, Schmidt-Huber suggests that this bridge can be better explained by giving commands to the reinforcement learning problems. So what's proposed in this paper bridges the gap by avoiding the issues arising from the combination of function approximation, bootstrapping, and off-policy training. Eloy, to go to your bigger question on what is the behavior function, here we do have a model-free or model-based algorithm, or in generalized agnostic version of a model-free or model-based algorithm for reinforcement learning, for upside-down reinforcement learning, where the trajectory is nothing more than a sequence of state, action, or rewards like this, which are sorted, which are given basically a loss function from time 1 to time 2, where we're given a state where we have a desired return given the desired horizon of the action. This is then given by the length from the trajectories. Here is a cartoon value of what the trajectory might be from any given time step, where the desired reward is snipped by the desired horizon.
One question I have is that in the previous slide that you had, the action was an input for the observation function, but now it's cut up for the loss in the observation function.
Yes,
I mean,
so that
logically it makes sense because the observation function is what you would be learning, right? That's like your neural network, for example.
Yes, so specifically, yeah, so that specifically is sort of the episodic data that is being stored from the behavior function. So the behavior is trying to learn and all given actions of that state and action pair, given the desired return and the desired horizon, and then ranking them and storing them accordingly in the repay buffer. Does that make sense?
Right. So if you go back one.
Yes.
you can kind of view the loss function as taking the behavior function with those inputs. It would create a hat T1,
Hmm.
and you're basically computing the loss function between the like the predicted state and the actual state, right?
Yes,
Okay, yeah.
great question.
Jay,
So
sorry.
yes,
Real quick question. So I'm imagining, you have like an Atari game or something. So would you basically, let's say you have left, right as your action, and then, the other pixels of the spaceship or whatever hitting you. And so you would cut up the movie into what the like one move desired return is, like one I don't know, one step to the left, maybe two would be a second desired horizon or whatever. And then so for each one of them you would compute a hat, as Eloy said, and then you would compute that versus what the actual action is. See, that's what's confusing to me.
yeah. So specifically,
Yeah.
instead of chopping up the sort of frames that you suggested, it's more indicative of what is the actual reward happening. So in Lunar Lander, for example, if you take any kind of, which here I can show you an example of that. Let me scroll to this. So this is an example of some of the games that they tested on. This is Lunar Lander, where specifically you have a negative reward for any time you use fuel, but you get a negative of like 0.03 for any time you use fuel. There's 4 actions you can take, either left, right, up, or down. But you get a negative reward of 100 if you don't land between the 2 flags, but you get a positive reward of 100 if you land on the flags. So given the desired horizon of actually either completing it or from the desired return, you're basically giving choices learned over time whether or not to take an action to get closer to this value or to this space or not. Where the problem is solved if you do actually get a reward of over 200. So the objective of the solving the problem is to get a reward of 200 rather than actually trying to solve sort of a stepwise pixel iteration or feeding the network in based off of images. Does that make sense?
If you give it like I want, the reward would be like 100, right? Between for example, between the 2 flags.
Yes, one
So if
detail
you
I
would,
did leave out is you start with a positive reward of 100 or negative or 100 or to 140 depending on where you actually start in this space.
right. So if you tell it I want a reward that is higher than 100 at the end within like 10 steps, let's say it takes 10 steps, then it would have to land in between those 2 flags, right? Because otherwise the actions that it predicts are not correct because it would get below 100 because it's using fuel.
Yes.
Okay. But so for example, would it also make sense to train it how to do it incorrectly? Like being able to predict like an action that creates, for example, 0 reward at the end, so you use a lot of fuel, does maybe make this function more expressive of also, okay, this is the incorrect way of doing things if you want to get a high reward, for example.
Yes, there are specific implementations of that with like Actor Critic or PPO that have attempted to use sort of a network to train on data that doesn't get best reward, but usually you're trying to maximize the reward function.
Right. No, it makes sense. But I'm just thinking about like making the network more aware of all the types of things it could do and sort of why it's like incorrect, right? It's like, okay, if you do this, that is not a good reward, but knowing that it is, maybe that helps the function understand what.
Well, so that's where upside down reinforcement learning actually comes into play that seems to start to alleviate that problem or that issue where you're actually learning best commands to do over time. So it's not necessarily trying to always find the correct action to take immediately, but it iteratively steps through which commands to best take.
Right. No, I understand. I'm just thinking about like if you also know what the bad commands would be, that would maybe like let's think about if human beings, like I know also what a bad command would be. You know what I'm saying? Like just from like human behavior, it would be, and maybe that leads to a better general understanding of the problem in the first place. Like the
Yeah, so
reason
they
why
do
I'm
they
good at
do
something is also because I understand exactly what would happen if I did the incorrect thing. You know what I'm saying?
so then you start to get into the problems of partially observable Markov decision processes, because this still assumes that we have full knowledge of the environment. One thing with that is you still don't know what all of the bad actions can be, and that table can blow up
Right.
very fast in terms of state
Yeah,
action pairs.
exactly. Yeah.
So what they've done is to do some more distributed algorithms that will take different batches of learning and then try to combine them based off of the best policies and iterations as well. And so at least sharing information is still an open question in the field. But to get back to that and sort of to go through the algorithm a little more generally, they start with a replay buffer, which is referenced to have these behavior function pairs with just a random actions to just soft start or warm start the algorithm. They initialize the behavior. They create stopping criteria, which is a hyperparameter as they move through the behavior function. Is then trained on the replay buffer, which is then iteratively updated to have the best actions given the specific state. These sample exploration commands are then based in the replay buffer, the episodes using algorithm 2 and adding to the replay buffer. And then if the evaluation required is met, then the agent will stop. To generate an episode using the behavior function, they initialize some C0, which is initialized as the desired return in the desired horizon of this, which then the state is initialized for the behavior function, which is parameterized by theta here. Then they store a episode data where they then compute the probability distribution of an action given a state and a desired horizon or desired return and desired horizon, which is equal to the behavior function given the set of parameters. They execute the action, obtain the reward, they append it to the episode data, and then they iterate on all of the variables in succession. This is done until stopping criteria is met or some kind of reward is met. For the explanation of what they did for design choices on how to rank this replay buffer, the number of episodes from the replay buffer has the highest returns. So they will then rank order all of the best returned actions, and then the exploration horizon is set to the mean of the lengths of the episode. So this was a specific design choice to help with computation and make it as simple as possible in terms of heuristic value as they were trying to decide what choices to actually make. And so the exploration returns the sample from the uniform distribution of the mean plus standard deviation, where M is the mean and S is the standard deviation for the selected episode return. So you might have hundreds of different connections or nodes that the agent might be able to take. And so this is a way of minimizing the number of actions in this table as you start to learn the algorithm. So for a second example, and a little bit more complicated, here we have the different states with the actions and weights with the terminal state S5 and S6. If we're trying to get to S5 for this example, the table would then produce these three sort of tuple pairings where you would go from S0 to S2 to S4 to S5. If we're trying to get from state 0 in 2 steps with 3 in a max amount of 3 steps. Or sorry, I said that wrong. State 0 with a reward of 2 with 3 desired steps remaining. That would give you the action of S or of A1 rather or A2 rather than A1. So going through this trajectory, we then look to see if we want to take action 5 or 6. Here they say action 5, and then from S4 we would take S or A7 to get to the terminal state. Additionally, if we were going to go from S0 to S6, we look to see the two different actions. Here we see that we're trying to get a resulting reward of 5, given a 3-step trajectory. We go to we take A2 instead of A1. I blocked this out, but I believe that is a 3 there. Then we take, I think it's a. I
It's a
put my
1,
cursor,
right?
but I
Because then you get
apologize.
5. It's a 1
Yeah.
because it's 1 minus 1, 5. Yeah.
Great. So same thing here. So it's just taking the action. So especially at state 2, we're trying to get a desired reward 4 in 2 steps. So instead of trying to go through this loop here, we're going up to S3 and then terminal state of S6 based off of this procedure. Hopefully that helps people understand what the choice action here is making and how it differentiates instead of just taking the maximum expected value or the maximum expected reward.
One thing that I'm wondering is from S0, you could also just take S1, S3, S6, right? That's also 5 reward in 3 steps.
Yes, that would probably be done based on exploration in given different seeds, and for your randomness, you're going to have different different runs, which is why the authors here ended up choosing 20 different seeds to attempt the algorithms on, which has a 95% confidence interval, which I'll show in later graphs.
I'm a little confused. Sorry. I'm a little confused what is given. So is this graph like the input and then it learns the behavior, or the graph is known?
The graph is known, yes. So this is a fully observed environment where each action has a reward attached to it.
Okay.
Does that make sense?
Yeah, so you basically like you have the graph and then you just figure out, what are the like long-term actions, or at least till like a certain limit. And then you just learn that. Okay.
Great. These are the hyperparameters for upside down reinforcement learning. We have the batch size, the fastnet option, which is a fast weighted architecture to try to go through some of the hyperparameters, either a gated or a bilinear search. They have a horizon scale. The last few are just the number of episodes from the end of the replay buffer used for the sample, the exploration commands, learning rate for the atom optimizer, number of episodes per iteration, and the updates per iteration, and then the number of warm-up episodes where they just are randomly searching through the whole system itself as the warm start to the replay buffer. They have the replay buffer size and then the scaling factor for the desired horizon output. With that, the games that they tested this on are 4 individual games that are very common in reinforcement learning. Lunar Lander, for example, is a simple Markovian process. All of these are enabled in the GYM reinforcement learning library, which is available on GitHub and is regularly used. During each, so just briefly going through it, Lunar Lander goes through each episode where the agent receives negative reward at each time step that decreases in magnitude as it gets closer to the optimal landing position. The reward at the end of the episode is either negative 100 for crashing or positive 100 for a successful landing. The agent receives an 8-dimensional observation and can take 1 of 4 actions. Take cover is the next one to the right, is a part of the VizDoom library. The agent is spawned next to the center of a wall in the rectangular room facing opposite walls where the monsters randomly appear and shoot red fireballs at the agent. It must learn to avoid the fireballs by moving left or right to survive as long as possible. The reward is +1 for every time step that the agent survives. So for the reinforcement learning always sets the desired horizon to be the same as the desired reward and converts any fractional values to integers. Each episode has a time limit of 2100 steps and the maximum possible return is 2100. Due to the difficulty of the environment, the number of monsters increases over time, and the capacity of the environment, the task is considered solved when the average return is over 100 episodes. which exceeds 750 reward. For swimmer 2, which is the bottom left here, and for inverted double pendulum 2, are environments available also in gym and based off the Mujoko engine, where swimmer 2 is the task to learn the controller for a 3-linked robot immersed in a viscous fluid in order to make it swim as far as possible in a limited time budget of 1,000 steps. The agent receives positive reward for moving forward and negative reward for proportional to the squared L2 norm of the actions. The task is considered solved when you have a reward of 360. Alternatively, in double pendulum, the task is balanced and is trying to imbalance an inverted 2-link pendulum by applying force on a cart that moves left and right. And the reward is +10 for each time step that the pendulum does not fall, and a penalty of negative rewards proportional to the deviation of position and velocity from 0. There's more details in the code, but the time limit for this is 1,000 steps, and the return threshold for solving the task is 9,100. To give examples, like I just did, on sort of what untrained learning looks like for some of these agents, we see that the swimmer is just kind of convulsing here, and the agent is just sort of falling, trying to do random actions, whether or not it can land properly or not. Going over some of the results here, these are results on tasks. So the top row with lunar lander and take cover are discrete valued actions that the agent can take, and the bottom row is continuous valued actions, as a swimmer can continually move, or the inverted pendulum is continually moving as well. The solid lines represent the mean of evaluation scores over 20 runs using tuned hyperparameters and experimental seeds from 1 to 20. Shaded regions represent 95% confidence interval using 1,000 bootstrap samples. Reinforcement learning is competitive, or the upside down reinforcement learning here, as they claim, is competitive or outperforms the traditional baselines on all tasks except for the inverted double pendulum. Here, they use the environments with both low and high dimensional visual observations. So with lunar lander, that's considered a lower dimensional observation, whereas take cover is a higher dimensional one, and both discrete and continuous valued actions. Going through, they compare all of these, or they compare these algorithms in the top row for discrete actions space with double DQN learning, which is the Min et al. Paper from 2015, which DeepMind used for Go initially, and then the Van Helsing actor or advantaged actor critic, or A2C, which is a synchronized version of the algorithm proposed by Min et al. In 2016 for environments with discrete actions. TRPO and PPO and DDPG are ways of conducting this in a continuous environment as well, using a couple different mechanisms that we don't need to get into due to time, but those are state-of-the-art algorithms, or near to the state-of-the-art algorithms, used to help agents learn in a continuous environment. The authors follow the recommendations to use separate Cs for training and evaluations, like we said, as the 20 independent experiment runs for all the comparisons. Sorry. They use, sorry. They also use a hyperparameter search to tune each algorithm before performing on the 20 seeds. All agents were implemented using a fully connected feed-forward neural network to make sure that it is a simple process to be able to compare with, where the only exception is take cover used convolutional networks to train. They were trained for 10 million environmental steps for lunar lander and take cover, and then evaluated for 100 episodes at 50,000 steps intervals. For the less stochastic swimmer and inverted pendulum, they used only 5 million steps and evaluated at 50 episodes to reduce the computational burden. What they found is that by simply concatenating the commands with the states led to very inconsistent results, making it extremely difficult to tune the hyperparameters. So they used architectures with fast weights, which Schmidt-Huber did in 92, where the outputs of some of the units are weighted by the other connections. So trying to learn off of past inference. This considerably improve the reliability over several runs. They chose two of the simplest choices of our hyperparameter search, gating, as we commonly see in LSTMs, and then bilinear search, using them only at the first reward state layer in fully connected networks and at the last layer in convolutional ones. This design makes it difficult to ignore the command inputs during training. To go over some of these results, on Lunar Lander, all the algorithms were successfully solving the task, reaching on average returns of over 200, which is the task goal. Upside down reinforcement learning is similar to DQN in this state, but both algorithms were behind A2C in simple complexity and natural returns, which benefit from the use of multi-step returns. On take cover, upside down reinforcement learning outperforms both A2C and DQM comfortably. An inspection of the individual evaluation curves show that both baselines had highly truncated evaluation, sometimes reaching scores, high scores, but immediately dropping the performance at the next evaluation. So here that is saying that there are good scores in some iterations, but at times when the agent, since the agent is randomly exploring, it might have a negative reward return. Well, it may be possible to address these instabilities by incorporating additional techniques or modifications to the environment. It is notable that upside down reinforcement learning does not suffer from the stochasticity. On Swarm 2, upside down reinforcement learning outperforms TRPO and PPO and was on par with DDPG. However, with DDPG, evaluation scores were highly erratic, indicating that there is a large confidence intervals, and it was rather sensitive to hyperparameter choices. It is also stalled completely on low returns for a few random seeds, while upside down reinforcement learning shows consistent progress, as you can sort of see by the smooth line here in the small confidence interval. Finally, on double inverted pendulum, upside down reinforcement learning was much slower in reaching the maximum return on average, as you can see. But compared to the other algorithms, which typically solve the task within 1 million time steps. Well, most runs did reach the maximum return of 9,300. Some failed to solve the task with the step limit, and one run stalled at the beginning of the training, is what the authors said. However, overall, the results show that while upside down reinforcement learning can concurrently lag behind the traditional reinforcement learning algorithms on some tasks, it can also outperform on other tasks despite its simplicity and relative immaturity of development. What the authors then decided to do next was conduct additional experiments to examine how upside down reinforcement learning acted as the reward function characteristic changed dramatically. Since upside down reinforcement learning does not use temporal differences for its learning, it is reasonable to hypothesize that its behavior may not change directly from other algorithms that do so. To test this, they converted the outer environments into a sparse delayed reward and thus partially observable versions by delaying all rewards until the last step of each episode. The reward, so what that means is that during an episode, temporal difference allows you to react to the given action in the state space to best correct for what is happening. Here, they decided to perform the whole episode and then take the reward of all of the actions given the state. A new hyperparameter search was performed for each of the algorithms on Lunar Lander. For the other environments, they reused the best hyperparameters, as this testing is computationally exhaustive, and they wanted to try to test for a denser setting. These are all the results from the 20 runs plotted with different seeds. The baseline algorithms at this point become very unstable and very slow, or fail to complete as expected. Simple analysis or simple tasks did not work, as they failed to train an LSTM DQN on Lunar Lander, while it still performs similarly to A2C on Lunar Lander. A2C with 50 or 100 time step intervals, the best performing baseline of this task, was very sensitive to these hyperparameters, but very few settings from this search space succeeded in solving the task. upside down reinforcement learning did not exhibit such sensitivity in its behavior across the hyperparameter setting, was comfortable with behavior for denser networks. It may be certainly be possible to solve these tasks by switching to the other techniques of standard reinforcement learning. Their aim in the paper was to highlight that upside down reinforcement learning retrained much of the performance in this challenging setting without modification by design. It directly assigns credit across long time horizons. On inverted double pendulum, its performance improved even when approaching the performance of PPO and other dense rewards. The upside down reinforcement learning objective simply trains an agent to follow the commands compatible with all of its experience, but the learning algorithm in the experiments adds a couple of techniques to focus on higher returns during training in order for it to make somewhat comparable to algorithms that focus on maximizing returns. This raises the question, do the agents really pay attention to the desired return, or are they simply learning a single policy corresponding to the highest known return? To answer that, the authors evaluated agents at the end of a training by setting various values of the desired reward to 0 and plotting the obtained mean episodes returned over 100 episodes. So this figure to the right shows the results of this experiment on Lunar Lander 2 agent, as it has a strong correlation of 0.98 between the obtained and desired returns. Even though most of the later stages of the training used episodes with returns close to the maximum, this shows that the agent remembered how to act to achieve lower desired returns from earlier training phases. We note that occasionally this behavior was created by the stochasticity in training, and some of the agents did not produce very low returns when commanded to do so. To further this, there is supplemental material in this first paper that outlines sort of different training agents given different times, where the desired return is a simple y equals x, and then trying to map that given a couple different runs of the parameters.
This is
I'm
kind of what I meant
pause.
as well. Sorry.
Yeah. I'm
This
going
is
to
kind of what
pause
I was.
here because I know I went through a bunch of the results. Do people have questions?
Well, yeah. So they're saying here, right, that like it's even able to create bad actions. So it kind of,
Exactly.
right, which kind of leads you to, I mean, it doesn't mean that it understands the problem per se, but it's a better measure of like, does it understand sort of the space of actions that it's in more completely than a network that is only trained using this kind of maximizing the reward, right?
Yes, because most of these algorithms are taking sort of a heuristic approach when iterating over a given episode and then trying to learn from the information throughout the whole episode in either distributed ways or types of policy gradient methods. So absolutely agree that it has a broader implication on long-term desired return for the horizon. Just for an example of, this is 2 episodes that were trained getting to 230 reward. It shows the 2 commands with the same desired horizon of 230 steps. And because the algorithm learns to go to the desired horizon, there is synchronization at the end, which is also interesting to note. With that, there is a bunch of related work, and I will post these slides if anybody's interested because it can get a little dense. But there are alternate perspectives on learning by acting directly, associating with good actions with higher control. There's episodic control, model-free algorithms that value with experience replay, or some kind of supervised learning routines, value functions and policy with goal conditioning, Monte Carlo style future predictions without bootstrapping. Arjona and Medina did gradient-based supervised learning in recurrent networks perform contribution analysis. There are task inputs and reinforcement as interference as well. And just due to time to not go through all of these, they make notes on how they differentiate and more generalized better than many of these algorithms in the discussion section. They also noted that when this was published, there is very similar work being conducted as well, where they have defined different groups have defined the objective to be very similar to the behavior function that Schmidt-Huber has been developing, where the algorithm always retrains from data from the current policy is using to improve the policy gradient estimation. Additionally, there's utilization of pure supervised learning to learn on a policy condition on the goals using the data, using a human operator to play in the mode. So it's trying to get a better bootstrapping if people are actually playing the device than rather a search or a type of searching method. Additionally, there are other conditions to have fixed goal states, and then the paper that they wanted to highlight, and they have a couple of paragraphs on, is that there's very similar work to upside down reinforcement learning, that the differences with the discount factor, instead of explicit horizon conditioning, they end up doing more of a replay buffer that stacks very slightly. Since these small implementation details can be made into larger differences in numerical results on best benchmarks, it's really difficult to compare the results across these studies. But they do have work that they've cited to explore this further, which the comparison to RCPR is introduced. Future directions and open questions. There's not really a great mathematical or theoretical properties with upside down reinforcement learning, much that traditional reinforcement learning has. So this is a big question, as traditional reinforcement learning has the benefit of decades of development into leading of various algorithms that can, under certain positions, provide maximized expected returns in arbitrary stochastic processes. Many real problem settings, while not deterministic, are not arbitrarily stochastic either, and learning agents should and likely can exploit these given different heuristics. Episodic control is a big field in reinforcement learning right now. There is the case of the deadly triad, where well-known issues arise when the off-policy bootstrapping isn't combined with a high dimensionality function, where the combination that Sutton and Bartow refer to as the deadly triad can lead to instabilities, which we saw in much of the results that can be addressed by adding a variety of the ingredients with upside down reinforcement learning. The complete remedies to this situation still elude the field in many of the current research. Avoiding temporal distortions. As you explore more, you might be gravitating to different actions based on this exploration, which can distort some of the gains that you've gotten from previous time steps. Limitations in various stochastic environments, as we saw in the VisDoom. It's very difficult because it's high dimension. And then potentially using more complex architectures in terms of a reoccurrent state for instead of a feed-forward neural network to observe more of the information from past observation and selected actions. And then there is also work to be done on reframing the problem as reach a given goal state in most t time steps, rather than having a desired return given a desired horizon. Always exploring more complex environments, and then a vast amount of possible combinations in reinforcement learning algorithms for temporal different learning, optimal control, and policy research. Potential applications that the authors wanted to note are specifically industrial process control, robotics, and recommended systems. And with 5 minutes left, without going into a little more of those details, I'll go ahead and throw it up for questions.
So how similar is it to previous work? Because it sounded pretty.
Yeah,
Fairly
so
close.
imitation learning is the closest thing to what I would say is upside down reinforcement learning. And in fact, there are
Mhm.
several Medium articles trying to compare imitation learning, which is the way of attempting to use more of a replay buffer or a way of trying to have the agent learn on its best sort of state action pairs in the given environment. And so it is trying to maximize at least learning from its past data. It creates another network within the problem itself. But what research has shown, and even test examples from these Medium articles, show that there is improvement by having a choice of the desired return given a desired horizon based on performance. So instead of just trying, I think most people are hypothesizing that's due to the stochasticity of the different environments. So a lot of this has been done on lunar landers since it's so accessible from Gym in Python, that the choice in having the choice of action is actually more beneficial than actually trying to learn from past data.
Right. That makes a lot of sense. And so they're saying that it's not, the real world is probably not fully stochastic. So do they envision that this works worse in real life?
They're suggesting that there's more research to be done within this field, but I believe by having the choice, given some kind of stochastic environment with some related properties, that it actually would be better in pursuit. And that's why they acted on those 4 different games to try to have both discrete action space, continuous action space, low dimensional and high dimensional space.
Right. I can also imagine, like you said, it's better in high dimensional space, but also that they wanted to look at doing this within a certain number of steps. And if you can figure that out, then I can imagine that it works much better in a real life scenario, because especially with robots trying to say you need to get there within 10 time steps, probably there is a lot of stochasticity then, or like a lot of ways that you can do that. And then it seems like this algorithm is able to use kind of that to its own advantage, right? With
Exactly.
how it's
Yeah, it's
trained.
exactly that. Especially when sort of you find that the algorithm ends up having a synchronization given the desired horizon. So like you said, for a very mood example, if we have a Mars rover that needs to get to point X to point Z to collect this rock, you want to make sure you get into there with a very specific amount of time, or else like the sun might go down or something. And that
Right.
might create a cold condition that would destroy the robot or something.
Right. Yeah, and so that's actually really cool. The fact that it's like that it's so usefully kind of uses the large action space to improve itself, right? That's basically kind of what it, like, I don't know. To me, it seems like it
Yeah,
understands the problem almost better, if that makes sense.
Elo,
Mhm.
didn't you present a paper about Schmidhuber where they were doing about dreaming and sleep? So it kind of is like a similar thing where he has that like weird like replay mechanism thing where he's like making use of like previous data to do. Yeah.
Right. To me, this kind of feels a little bit more human, because let's say this robot, right, decides to either go, like for this example, you want to go to the same space in your head, like as a person, you kind of envision the roads. Like let's say, oh, I want to, get to the station by 10, right? Because that's when the train leaves. You kind of think of like, okay, I can go there walking, and if I go walking, I couldn't go like this way, this way, this way, this way, but probably this one is the best. This sort of the large action space that you have to reach a desired reward, which is catching the train, and a desired horizon, seems a little bit more, in some instances, not always, but in some instances, a little bit more how humans approach a problem. Like this
Yeah,
lunar
I mean,
lander.
I would even like say something like simple, like grabbing a water bottle, like you're trying to, you kind of know when you're getting there, and like you have so many different muscles, and
Right.
you've never really learned your muscles, but
And it's
you
probably
kind of
not
learn.
optimal. Like, grabbing the water bottle, there's so many ways to do it
Yeah,
Mhm.
that you can have a little bit of so like it doesn't matter if you don't do it perfectly every time.
yeah,
It's more
yeah,
about like the sort of, well, like you said, the end reward and the end horizon. That's the thing that you want to learn, basically. That's what.
Yeah, you don't
I
want to
think
get there
also-
too fast and knock it over or something. So
Yeah, the thing that I haven't done is looked up the current state on archive or even like NeurIPS from last year to see what has been done to try to alleviate some of these problems or how it can best benefit a more of a robotics or control setting. Because I completely agree. I think that this has been a big topic in reinforcement learning in the last year and a half. And even talking to some of the other TAs in the reinforcement learning class who specialize in this in more commercial work, they haven't fully gone into this because they think some of the algorithm parts are kind of cute based off of the notation and they just haven't looked at it yet.
Right.
So
Yeah, I can also understand that if you want to be in like that, yeah, like in commercialization, it doesn't make sense to try these new types of methods just because it's like, we just want
there's
something.
still a lot to be done theoretically.
Right, exactly. Yeah, exactly.
well, it's really weird that that like different algorithms outperform on different games, which is kind of there was like no like king like that just destroyed everything.
Yeah, there
Um,
really
which-
isn't. And
which
that's
is
really
really
because
weird.
of how it's really based on the environment and the reward structure you give. So most of the algorithms in this aspect can perform better on continuous environments. Some don't even have the capability of doing continuous environments. If you're on policy or off policy, depending on how you optimize your gradient descent, they'll perform better or worse in various environments, which is a huge open question in reinforcement learning.
Doesn't that also make sense for your brain? That different brain pathways code for different types of problems slightly? Like it wouldn't make sense. Like our brain probably has like a multitude of ways to kind of approach a problem through shared pathways, right? And I don't think it would be weird that your brain uses a slightly different pathway through like your basal ganglia or something to do discrete problems in like gaming than it does when it's grabbing a water bottle. You know what I'm saying? Like I don't think it would be weird that there is slightly different like algorithms.
Yeah,
that-
like slightly different specialized hardwares that where one
yeah,
is
exactly.
doing a more continuous problem and the other
Right.
one's
They're
doing a
probably
different
shared,
algorithm.
right? Because the brain
Yeah.
is super shared. But I wouldn't be surprised if there's like just slightly like
Yeah, I guess it's kind of weird because I was just hoping there's, I mean, you just like get one algorithm that just solves RL, or I mean, not all of these.
where's my
but, like,
So, I mean,
RL?
Armin, if you are looking for something like that, it was temporal difference back in the day in '88 that Richard Sutton ended up coming with, and temporal difference was the be-all end-all for reinforcement learning. But then they found that it doesn't generalize to all spaces, and then it becomes computationally so stressful as you start to get to Q learning, where you have the table of action state pairs, and then you try to learn that action state pair table with deep Q learning or DQN, which is sort of the state of the art from 5 years ago that DeepMind used to solve StarCraft, chess, Go, shogi.
What I just thought about, to quickly go back to Amrit's first point, it would actually be fun to see, like, as we progress, that certain types of algorithms work way better on certain problems than others, and that we actually relate those types of algorithms back to our brain. So, like, if we do the grab the water bottle, we would suppose probably that there's a different type of algorithm that works better than if we were to do like Atari, right? Like clearly better, and then relate that back to our brain. Like, how does our brain have probably a different pathway for playing Atari than it does grabbing a water bottle? I mean, that makes sense because it's like different types of motor control and different types of abstractions. But that would actually, I think,
so I would probably split that the what you just said into two different places, Eloy. One, because you're resource based, given different sections of your brain. And so
Right.
you're going to need to implement different algorithms based off of those resources to best optimize for that information share. The second
Right.
would be potentially even evolutionarily why we would even have these resources in general. And that could be very interesting to see how it develops as well.
Right, exactly. Because I'm kind of thinking about the research that they do with like convolutional neural networks and see how, I mean, you would not be able to do this at the same level that they do for convolutional neural networks, but you can see the neurons firing for the same type of images in like V1 as like the first two convolutional neural layers in a convolutional neural network. But I would imagine that it's really cool and interesting that if we can go towards that type of stuff, to see whether certain algorithms seem to code the same way, like best performing algorithms for certain problems in RL code similarly in the brain.
Yeah, that would be very interesting.
I mean, it's very far away, right? It's not something that you just like arbitrarily do or something, but it's
Yeah, yeah.
like,
But
for example, if
these are
you
great
view the
questions.
brain very abstractly, let's do like EEG, like the pathway that you sort of take while grabbing a water bottle. I think we have those types of things like motor control. We can kind of see
Mhm.
how the electrical activity runs through the brain. And if you view these like structures in the brain more abstractly, can we find similarities between reinforcement learning algorithms that perform really well in these tasks? And we don't have them yet, right? Because we're still very much learning how to do these type of things. But when we do clearly have some kind of winner per task, can we relate them back to the electrical pathway that we see throughout the brain? Like, I think that would be really
Yeah,
cool. Also, because we can see like whether we do this type of stuff, like this upside down, or if it's more the temporal difference, or if it differs per task. You know what I'm saying? Like maybe we do temporal difference for some tasks and we do upside down learning for others.
yeah. Because I agree that we have a lot more conditioning as humans with different subtasks on exploration versus exploitation, where we are able to learn faster, in much faster than any of these algorithms based on whatever processes are going on. And that's just a relatively open question as well, and how that is working.
Yeah,
But
I
I
mean,
know
I
that
would. Oh, yeah, go
sorry,
ahead.
I know that
Yeah,
we're
it's
over
fine.
time. Yeah. I love this conversation, but I definitely want to let other people go if they need to. Um,
Yeah, we're kind of over time. We started 5 minutes later, and now we're 3 minutes over extra 5 minutes. So thanks, thanks TJ for the talk, and thanks everyone for discussion. Maybe we can continue it online, offline. I mean, next Friday, not the next Friday. Next Friday is Thanksgiving. We won't have a meeting, but the Friday after. Sajjad will give us a tutorial on answer set programming, a very powerful tool that we overlook and many people can use it, I believe, if you knew about it. So let's wrap up here.
Great.